Hello class, today we're going to learn about the tangent function. So how does a tangent function relate to the unit circle? So the tangent function is basically the slope of the terminal arm. And this is because if you recall the tangent equation using x, y, and r definitions is tan of theta is equal to y over x. This looks very similar to something you've learned for many years, which is that the change in y over the change in x, which is basically the rise over the run, which is also what we define as slope, which is why the definition of a tangent function is talking about the slope of the terminal arm. So here we have a diagram showing the initial arm and a terminal arm. And so the tangent, when we talk about slope at this initial arm, the tan value would be 0 because the slope would be 0. But then as it moves up around the circle, it'll start gaining value. And then there's something interesting that happens when the tangent, the terminal arm is at the 90 degrees here. The slope of this arm, if you recall, a straight vertical line, would therefore be undefined. So therefore, this would lead to asymptotes in a tangent function graph. This happens at the 90 degree, which we see here, but it can also happen as you continue forward into the 270 degree, so when it's below. But it also happens if you go in the negative degree side, which would be negative 90 as well. And as you can see, it pretty much happens every 180 degree rotation from the 90 degrees. So the tangent will have asymptotes. Okay, so now let's use our knowledge of the tangent function to determine the exact value of various angles. So as we look at tangent of 135, remember we always try to do a sketch to see which quadrant it's in, and 135 is over here. And so when we look at this, we look at the slope. If you look at 135, that's basically on a 45 degree angle from the 180 side, and so a 45 degree angle means it's that perfectly diagonal line, and so the slope would therefore be so if we look at the relative acute angle here, beta is equal to 45 degrees, that this slope would therefore be just 1, but negative 1, sorry, because we're going from left to right downwards. Okay. Tan of 270 is what we talked about earlier. That's when the line is straight vertical downwards, and a vertical line up and down will have a slope is undefined. And so that's what the value of tan of 270 is. Tan of 180 is when the line is straight horizontal going to the left, and that slope is 0 degrees, or 0, sorry. Whereas a cotangent of 225, well, where is 225? That's down here. Okay, and then again, here's our slope. This is the relative acute angle here is 45 degrees. And so the slope of 45 degrees, a straight diagonal, would have been 1. But remember, cotangent is really 1 over the tan of 225 degrees. So that's really 1 over 1, because that's our slope, which is still 1. So the cotangent of 225 is still 1. Now that we've looked at a couple of tangent values, let's try to graph this tangent function on our Cartesian plane. And so when we graph this, we'll find out that, as we saw At 90 degrees, we saw that there were asymptotes here. And then again at 270 because of the vertical lines. And then again at 450. And we said at the negative angles as well, so negative 90, negative 270, and negative 450. What happens at the other part? Well, we said that when it was a straight horizontal line, like 180 or at 0, you would have a 0 slope. So then we would have a point at zeros, at 0, at 180, at 360, at negative 180, and negative 360. And then when we looked at the 45-degree angles away from there, we saw that the value was 1 or negative 1. And then here again, we'll continue that, like repeating periods. We'll find those same values at the other relative acute angles of 45 degrees. So what does this look like? Well, if you were actually to calculate all the in-betweens, you end up finding that the tangent function looks something like this. Almost that cubic function look, right? And it goes and avoids the asymptotes up there and down there. And it just repeats every 180 degrees. And so you can keep drawing these, but the tangent function looks something like that. Okay? And one more here. Alrighty. And that is our tangent function. So again, the asymptotes happen at all the undefined spaces. We have x is equal to negative 90 here, x is equal to 90. I'm just writing the equations for all my asymptotes. X equals 270, x equals 450, x equals negative 270, and again at negative 450. All right, so now let's just keep in mind, so what are the key characteristics of this tangent function graph? Well, we said that tan of x is equal to 0 at 0 degrees, 180 degrees, and 360. So whenever it's straight horizontal, whenever the line is straight horizontal, going this way or that way, is when we have a 0 value. And then we have, so these are horizontal, terminal arms, okay? The other case is when tan of x is equal to 1. That happens at the 45, 2 to 25, and etc. So again, whenever it was in this quadrant here, or this quadrant here, sorry, that should be straight lines. And then the other option is when tan of x is equal to negative 1, and that happens at the 135, 315, which is when it is the terminal arm going this way in the quadrant 2 and quadrant 4. That should be straight 2. Okay, so those are the key points of when we should define our tan function on the graph. And so now let's write those characteristics we need. So when does asymptote occur? That happens when tan of x is undefined, which we said happens in vertical lines. When the terminal arm is vertical, and that happens again. If we list all these ones, we have negative 270, negative 90, 90, 270, etc. All right, so how do we write the domain of this function? Well, the domain would say that it's x is the set of all real numbers such that x is all the numbers except at the asymptotes. So we'll list all the asymptotes. It's not at 90, 270, and we can just do a few of these and then end it. Okay? The range, well, if you look at the graph, it's all the y values, so we'll just say that y is a set of all real numbers. And the period we can see is repeating every 180 it repeats. Okay? If you remember, this is very different than when we talk about the sine or cosine. So for sine and cosine, the periods happen every 360. And so whenever we had to write the equation, it would be 360 over b for sine or cosine. But for tangent, this is now different. It is at 180. So we write period is equal to 180 over b. Okay? So this is going to be different. So keep that in mind, that this is a different period equation now. All right, let's graph this using this example. We have to sketch at least two cycles of the function y equals 3, 10, 2x minus 90. Now, please, hopefully you remember that for this graph, you need to factor out this b value. This b value must be factored away from the horizontal shift. So really what we need to do is write the equation of y equals 3, 10, in brackets, 2 bracket x minus 45. By factoring out, we see the true shift, which is 45, that is not 90. Okay, and now I would recommend that you use a mapping rule to figure out this equation. So if we write the original y equals 10x and put the key points here, x and y, we have at 0 degrees, it's 0. At 45 degrees, we said it's 1. At 90 degrees, we said it was undefined. At 135 degrees, it's -1. And at 180, it's back at 0. So now we're going to map this onto our new equation. So our x's and y's are now changing. According to the transformations, according to this equation, we see that x is getting halved because of this horizontal dilation by a half. Then it's getting moved over to the right 45 degrees. The y value is getting multiplied by 3 because there's a vertical dilation. All right, so if we go and apply this, you'll see 0 plus 45, so this is not 45, and 0 times 3 is 0. This is 45 cut in half. Add in 45, you're about 67.5 degrees, and then 1 times 3 is 3. At 90, cut in half, is 45 plus 45, you're back at 90 degrees, and it's still undefined. Because undefined times 3 is still undefined. 135 cut in half plus 45 is approximately 112.5 degrees, and then 3 times -1 is -3. 180 cut in half is 90, 90 plus 45 is 135 degrees, and then 0 times 3 is 0. So applying those points in here, well, let's do our asymptote first. So at 90 degrees, still there. And then we still have, we have a point, our 0 is down here at 45. And then what we have here is our stretch factor of 3. So then our next point will be at 3 and halfway between the 0 and the asymptote. And then again, the other asymptote was now here. And halfway between that would be our 3 because it was vertically dilated by a factor of 3. And so we have our one cycle of a tangent function right here. And that makes sense if we think about how our period now has changed. And so here's our period, which is 180, that used to be divided by 2 because of our horizontal dilation. So now it should be at 90. So we can draw a second one to continue this cycle right over here. And there you have it.